want to spend one lesson working through a simple neural network algorithm in Python without using libraries. It's worth noting that the general availability of powerful and flexible libraries for specifying and using machine learning algorithms has been one of the reasons behind the explosion of interest in machine learning. The programming language Python has been a very popular home for most of these libraries due to Python's widespread use and extensibility. One Python library that includes a wide variety of machine learning algorithms is called scikit-learn. It was first released in 2007. We used the scikit-learn library in the two previous lessons for training decision trees and simple neural networks. We'll continue using scikit-learn extensively throughout this course. But when we get to deep learning systems, scikit-learn lacks the flexibility and hardware support for building and running cutting-edge systems. For deep learning, the main library we'll use in this course is Keras, developed in Python by an engineer at Google, where it was optimized for rapid prototyping of cutting-edge learning systems. TensorFlow is another deep learning library developed at Google, and we'll be using Keras in a way that's layered on top of TensorFlow. Both were first released in 2015. As we use Keras, little glimmers of TensorFlow will show through in a few of the later lessons. We'll look at some advantages of PyTorch, a deep learning tool released by Facebook in 2017, in the final lesson of the course. These are all freely available libraries written to take advantage of powerful hardware, and they incorporate the latest optimizers and network architectures. It's not too much to say that one of the drivers of the deep learning revolution has been that everyone is welcome and everyone can contribute. However, these terrific libraries that make it so much easier to get started can also contribute to a feeling that the machine learning algorithms are inscrutable black boxes. That's why I want to spend one lesson working through a simple neural network algorithm in Python without using libraries. Let's start by returning to the green screen application we saw in the first lecture of the course. The algorithm we'll develop is a simple neural network called a linear classifier. A linear classifier is a rule that predicts the class of a given instance by taking each feature in the instance, multiplying it by a feature-specific weight, summing up the weighted features, and then checking if the total is positive or negative. The green screen image is a still of me talking about green screen images in front of a green screen. What we want is a classifier that can label each pixel of the image with whether it is part of the green screen or whether it is part of me in the foreground. For conceptual simplicity, we'll consider each pixel in isolation. More accurate classifiers might include information about the surrounding pixels. Our classifier takes a pixel value as input, the amount of red, green, and blue in the pixel's color, and it should output true if the pixel is part of the green screen, and false if the pixel is part of the foreground image. One reason that this problem is hard is what we see as green is actually thousands of different shades of green. Literally thousands. So our classifier needs to generalize across the many possible shades. We'll write code to grab a copy of the example green screen image. That will give our program a file to refer to. Once again, I'm using a web-based Python service hosted by Google called the Colaboratory, or Colab for short. For doing numerical computation, we'll import a Python library called NumPy, which is used by many of the machine learning libraries. Import NumPy as NP means we'll be able to use the shorthand NP to refer to elements of the NumPy library in what follows. Next, we'll run from keras.preprocessing import image. That means we're getting a piece of the keras.preprocessing library, specifically one called image. Yes, Keras is a machine learning library. Yes, I said we would not be using machine learning libraries for this lesson. The image sublibrary has some very simple programs for dealing with images. I promise we won't cheat and use any of the machine learning functionality of Keras in this lesson. The command image.load_img lets us name an image file and get its data. The image file is the one we just copied. We're storing the data in the variable img. Running the Python command display on img causes the image file to be displayed. Hey, I know that guy. The image data type is great for displaying, but awkward to compute with. Fortunately, the image library lets us convert the image into an array of pixels, which is much more convenient. We can run img_2_array to convert the image into an array. We'll call it R for short. Since the screenshot image has a little bit from another window at the bottom, we should clip that off. The command r equals r bracket colon 697 comma colon bracket selects a sub-rectangle of the pixel array up to row 697. We assign it back to the variable r. To see what the resulting image looks like, we can use the image library to turn the array of pixels back into an image data structure for display. The flag scale equals false means we want the pixels displayed as is. Without this flag, the conversion scales the image brightness, so it uses the full range of values. Notice that the weird little strip at the bottom is gone now. We're going to apply supervised learning to create a classifier that assigns green screen pixels to the positive class and foreground pixels to the negative class. That way, the positive pixels in the image can be replaced by a background image. For a program to learn this difference, we need a training set with both positive and negative examples in it. To construct this training set, we can identify a rectangle of pixels that is definitely green screen and a rectangle of pixels that is definitely foreground. Let's talk through how to use code to build up a training set. The left side of the image is all green, so let's grab that to serve as a set of positive examples. The reshape command in NumPy allows us to take this two-dimensional image and reformat it as a list of red, green, blue triples. Reshaping doesn't change the content of the array, but it does change the form in a way that's worth discussing in more detail. In Python, a number is a number, but you can also reshape it to be a list of length 1, or a 1x1 array, which is a tiny two-dimensional array. Let's take the number 3 and make it into a NumPy array. We can ask its shape or dimensions. We get back an empty list. This particular 3 is just a dimensionless number. Let's reshape this number into a list. We tell the reshape command to take x and make its shape open paren 1, comma, close paren. The comma here is just a signal to Python that we're talking about the list that contains the number 1. If we leave the comma out, it thinks the parens are just there to group the expression. Anyway, the variable x_list now contains that same 3 as before, but it's been reformatted as a list of length 1. Well, let's make a list of 3 numbers, 56, 28, and 0. The shape of this list is left paren 3, comma, right paren. That is, it has 1 dimension and the size of that dimension is 3. That's a list of length 3. This particular triple of numbers happens to be the red, blue, green colors or values of the color brown. And it's not just any brown, it's the official brown used by sports teams at my university. It's brown brown. Go 56-28-0 Bears! We can think of this list as being a pixel, one picture element of an image. It gives the recipe for making a specific color. So 3 numbers together is a list or a pixel. Its shape is 3. The shape of the 1215 by 697 green screen image of me is 697, 1215, 3. Reading right to left, we can think of the image as being made up of pixels, which are groups of 3 numbers. The pixels are arranged in lists of 1215 pixels, which make up a row, and 697 of these rows make up the entire image. So the shape is 697, 1215, 3. Returning back to our subrectangle from the green screen image, we selected a part of the image that consists only of the color green. The shape of this temporary array, temp, is 697, 360, 3. It's the full height of the image, but narrower. Temp is a 3-dimensional array, representing a 2-dimensional array of pixels. What we want is for it to be a list of pixels. That's also a 2-dimensional array, but one with 1 dimension for the length of the list and 1 dimension for the 3 values that make up each pixel. The reshape command takes the array of pixels and turns it into a list of pixels. The 3 in the list means we want the shape of the resulting array to have a 3 in the second position. The -1 in the shape gets filled in by the reshape command to be whatever number is needed to account for all the data. That is, it computes the length of the list on our behalf. The resulting list is 250,920 pixels. Now that we've captured a bunch of background pixels and made a list out of them, we can again use an array access with bracket notation to collect a diverse rectangle of pixels in the foreground. We've got a yes list consisting of green pixels and a no list consisting of foreground pixels. Now we're in a good position to construct our labeled training set. NumPy's concatenate command takes a list of arrays and glues them together into a bigger array. We'll form an AllDat array that is all of the data, all in one list. To make sure we can keep track of the green screen yes pixels and the foreground no pixels in AllDat, we'll make a list of labels. It consists of a 1 for each element in the yes list and a 0 for each element in the no list. NumPy provides the commands 1s and 0s that make an array of all 1s or all 0s with the given shape. We concatenate them together to get the overall list of pixels, or labels. Next, we'll design a program to learn from this data. A machine learning program has 3 parts: a representational space, a loss function, and an optimizer. The data we collected forms the cornerstone of the loss function. And because pixels are low-level sensory data, a good choice for the representational space is a simple neural network. Our network takes in the pixel colors as 3 numbers, R, G, and B. We'll multiply each of the 3 numbers by corresponding scaling factors, or weights, WR, WG, and WB. These weights can take on any values, 100 times red, a tiny fraction of green. Notice that the color pure white is 0, 0, 0, so any setting of the weights will cause pure white to have a weighted sum of 0. To make sure white can be classified flexibly, we include a bias weight that shifts the sum. Here, that means we'll include a 4th number, a constant C, that will get added into the total. Now we're ready to add everything up. We'll say the rule outputs green screen if the total is greater than or equal to 0. If it's less than 0, then it's me in the foreground. The representational space, then, is the set of all possible values for WR, WG, WB, and the constant C. Selecting specific values gives us a linear classifier rule for classifying pixels. What we've built here is a neural network consisting of a single output unit that takes in the pixel values and outputs a value used to make a classification decision. It's a pretty simple network, but it's more expressive than you might think at first. For example, let's say we want to classify any pixel as green screen if the value of the green component, G, is bigger than the sum of the other 2. Setting the weight for red to -1, the weight for green to 1, the weight for blue to -1, and our constant C to 0 captures this rule exactly. -R plus G minus B is greater than or equal to 0, so the green component G is bigger than the sum of red and blue. For a loss function, we want something that scores a rule as having low loss if that rule agrees with the examples in our labeled dataset. We can break down the loss for the entire dataset into the sum of the losses for the labeled instances. So that leaves us the problem of defining the loss for each labeled instance. An instance is a pixel color, values for R, G, and B, along with a 0, 1 label indicating green screen or foreground. A rule is the weights WR, WG, and WB, and the offset C. If the output of the rule on that instance matches the label, we want to have 0 loss. Otherwise, we can record a loss of 1. That's the sort of thing we want. Loss grows when the rule doesn't fit the data. But the inequality in the rule is kind of awkward. It would be nicer if we were working directly with numbers. So we'll restructure the loss function a bit. We can do that because the loss function is something we're choosing. We want to set things up so good rules get low loss, and we have freedom to decide exactly how to make that happen. To restructure the loss function, we'll make use of a sigmoid function. We saw the sigmoid function last time, and the sigmoid function takes any input from -infinity to infinity and maps it to a number between 0 and 1. At -infinity, it starts at 0, then as the input approaches 0, the output starts to get bigger. At 0, it crosses a half, then it approaches 1 as the input grows toward positive infinity. The sigmoid has the nice mathematical property of being a function that returns something between 0 or 1, just like the label. And in this case, we're only using the sigmoid once, so the expense of the sigmoid is not very significant. Now we can do one more trick. We want the sigmoid expression to match the label. Subtracting the label from the sigmoid expression gives us a value of 0 when they match, and then either -1 or 1 when they don't match. To make the sigmoid expression minus the label look just like the loss we wanted, all we have to do is square it. That leaves the 0 alone and the 1 alone, and it turns the -1 into a positive 1. The loss becomes the difference between the value that the sigmoid expression returns and the value from the label. Now, let's translate the loss function into code. That will give us everything for a complete machine learning setup except the optimizer. We're doing supervised learning with a labeled dataset, where the pixels of green screen background are labeled 1 and anything in the foreground is labeled 0. We've got a neural net representation space, 3 weights and an offset pushed through a sigmoid, and we've got squared difference on the data for the loss function. To make the data a little easier to work with, we'll add a 4th column to it. The column consists of all ones. Setting it up this way means we don't have to handle the constant C in any kind of special way. Instead, we can just think of it as a weight, WC, that gets multiplied by 1 before it is added to the total. Now our data has 4 columns, and they correspond to the 4 parameters in our representational space: the weight for red, the weight for green, the weight for blue, and now the weight for the constant 1. To compute the loss, we need to multiply the 4 weights by the 4 values in each of the data points. Because of the way we arrange the data, we can use standard matrix multiplication to accomplish this calculation. It multiplies the weights by the data and sums exactly the way we need it to for our rule. The matrix multiply leaves us with this list with 1 value for each of the instances in our data. In Python, the NumPy function matmul does the matrix multiplication. We then transform the resulting list of values using the sigmoid. It just so happens that the sigmoid function is 1 over 1 plus e to the negative input, so that's how we'll transform the value. To complete the loss calculation, we look at the difference between the output of the sigmoid, y, and the list of labels, labs. We square each difference, then we sum up all of these squared differences. Our loss function can now give us a score for any set of weights we choose. Let's try a couple of random weights and see what kind of values we get. We'll repeat things 10 times. Each time, we'll pick a random vector of 4 weights. The random function returns values between 0 and 1, so I doubled them and subtracted 1, so all the weights are now between -1 and 1. We'll print each of these weight vectors along with the loss we compute. Because of the random choices in this code, when you run it, it'll come out somewhat differently. But the overall pattern should be similar. We get a wide range of loss values. Here, the largest is over 280,000, and the smallest is around 37,000. That's a somewhat wide range. Randomly picking weights and seeing which leads to the lowest loss is already a kind of optimizer. It's not a very good one, though. Even the weights that gave us our lowest loss of 37,000 can probably be improved upon. But how? Because our loss function is expressed in terms of a set of continuous functions, we can optimize using an approach known as gradient descent. That is, we can use basic differential calculus to find the direction to move the weights that decreases the loss the fastest. So relatively quickly, we should be able to arrive at a set of weights where the gradient is nearly 0 because the loss function has gone flat. At that point, no further local improvements are possible, and we've reached a local minimum for loss. You can think of this process as follows. Consider any of the 4 weights that make up our rule. If we set 3 of them to fixed values and let the other one vary, we have a one-dimensional function mapping the choice of value for that weight to the overall loss that our loss function outputs. The curve for varying the 4th weight in our example has a nice smooth shape with a minimum loss for a weight value around -0.9. The idea of gradient descent is that the slope of the function at any point tells us which direction we need to move to find the minimum of the curve. For a weight value greater than -0.9, the slope is positive, so we need to decrease the weight value to decrease the loss. For a weight value lower than -0.9, the slope is negative, so we need to increase the weight value to decrease the loss. In general, we want to increase the weight value by the negative of the slope. Gradient descent carries out these slope calculations. It computes the gradient for all the weights simultaneously. This computation allows an exact update for all the weights to be calculated. The gradient for this particular example of a linear classifier with a sigmoid slope is known as the delta rule. Greek letter delta is a very common symbol for indicating a change or difference. So the delta rule says that each weight should be updated by taking the difference, the delta, between what the rule outputs for an instance and the true label for the instance. The difference between what the rule outputs for an instance and the true label for the instance is written y minus L. That difference is then multiplied by the derivative of the sigmoid, g prime of s. Then all of that is multiplied by the input value to the weight, x sub I. The resulting value is then scaled down to be a small number by multiplying by a learning rate, alpha. These delta W differences are then summed up over all training examples to produce a total change for the weights. This total change is subtracted from the weight to move down the gradient. To apply the delta rule to our problem, we'll define a subroutine called fit. This subroutine will take as input an initial set of weights W, the data instances, all dat, and the labels labs. It will produce as output a new set of weights with low loss. We'll be iteratively updating the weights by computing the gradient and then moving them a step in that direction. The critical line of code is the delta rule itself. Let's read it inside out and see how it is expressed in code. Labs minus y is the difference between the true label and the output of the rule. That difference is multiplied by the gradient of the sigmoid, which we compute by taking e to the minus h using the numpy function np.exp and multiplying by y squared. Those values are reshaped into a matrix, which is multiplied by the input data, all dat. Finally, np.add.reduce sums up all the recommended updates over all the training examples, resulting in a vector of accumulated updates with one component for each of the weights. We're going to iteratively change the learning rate, alpha, to make it bigger, but we'll avoid taking steps that are too big and cause the loss to increase. The variable done starts off false and is set to true when we discover that any further step to decrease the loss is too small to be worth it, which I defined as a decrease in loss of less than 0.0001 for this problem. We'll loop until done. In the loop, we'll flip a weighted coin. We'd like to monitor progress, so about 1 out of every 100 iterations, we print the weights, learning rate, and loss. Next, we take the gradient of the loss function with respect to the 4 weights. The calculation is very similar to what we talked about when we were computing the loss. When these calculations are done, delta W represents a direction to move the weights that decreases the loss the fastest. We can take a step in this direction, but the size of the step is important. If we take a very small step, progress will be slow. If we take too big of a step, we might reach a set of weights where the loss is increased. Professional grade optimizers work very hard to get this issue right. For the purposes of this example, we'll do something relatively simple. First, we compute the current loss, the loss we get with the weights W. We want to improve on this loss. Next, we double alpha with the hope that we'll be able to take a big step. Then we calculate the new weights, new W. They're just the old weights plus an alpha-sized step in the delta W direction. Now we check, is the loss with the new weights any better than the loss with the old weights? If the new loss is better, we skip the while loop. Otherwise, we assume we must have taken too big of a step. Let's halve alpha and try again. But there's no need to keep halving alpha forever. At whatever point alpha times the largest component of delta W becomes very, very small, we'll declare ourselves done. We've reached something like a local min where the reasonable step size is vanishingly small and the learning rate is just about 0. Continuing longer, even for huge amounts of additional time, would scarcely improve the loss at all. Our solution is locally optimal. We print alpha and delta W just to see our solution. But until the new alpha we picked gets very tiny, we once again recompute our new weights and go back to the top of the loop. After the loop, if we're not done, we set W to be the new weights, the ones that gave lower loss, and we return to the outer loop to search for more improvements. Finally, when the loop is done, we return the weights we ended up with. It's a relatively simple implementation of a gradient descent optimizer. It is specific to this particular representational space, weights for each component of the color. It's also specific to our chosen loss function, squared error of the sigmoid of the linear combination of the color and the weights. Machine learning libraries provide more general implementations that let you choose other architectures and loss functions without having to re-implement the optimizer for each one. Let's look at our optimizer program in action, starting with some random weights. We start with a loss at 23,008, and now you see the loss drop immediately to 492, and then gradually work its way through a few hundred iterations down to 404.7 when the procedure finally stops. Also printed are the weights W, and we can see that they have changed a fair amount. As we might have guessed, the largest magnitude weight, 0.11, is on the second component of the weight vector, green. After all, the classifier is trying to recognize any of the thousands of shades of green that might be visible on the green screen. The red component is strongly negative, almost -1, indicating that red very rarely has any part at all in green screen pixels. Conversely, blue has become only weakly negative, indicating that the presence of blue in a pixel is only an indirect indicator that a pixel is part of the background. So it looks like our optimizer is doing pretty well at reducing our loss on the 2 rectangles we took from the image as our training set. Or is it? With neural networks and most machine learning approaches, it's difficult to interpret the loss in absolute terms. What really matters is whether the solution found using the training set data also performs well on the original problem. Let's write a routine that can take the weights learned from the training set and use them to classify all the pixels in the original green screen image. We'll make the green screen white and the foreground black. Ideally, it should pick out my silhouette and the card over my heart. To apply the classifiers to the pixels in the image R, we need to first flatten out the 2-dimensional array of pixels into a 1-dimensional array, a list of pixels. We concatenate a 1 onto each of them so that we can apply the classifier to each. A matrix multiply of the image pixels with our weights W produces a set of numbers. Our rule is that negative numbers are foreground and positive numbers are green screen, so we threshold at 0. We reshape the resulting list of Boolean values so that we can concatenate the list with itself. Each entry of the list is now 0, 0, 0 or 1, 1, 1. We reshape this list to make it the same shape as the original image R. Finally, we display this image on the screen. We allow the conversion to scale the values so they become 0, 0, 0, black, and 255, 255, 255, white. Classifier does a pretty nice job. You can see me, all in black. There's maybe a speckle or 2 on my belt and around my waist. These speckles will allow the green screen to show through, which is not perfect. There's also one small black streak across the bottom of the image that corresponds to the edge of the actual photo. To get these right, we could add more examples to our training set and trim the image more carefully. But overall, it works. We can put me into any scene we want now. The gradient descent optimizer we built is somewhat brittle, it can be slow to converge, and it occasionally encounters numerical instability when it tries to exponentiate numbers that are just too big. Most importantly, it was written only for the specific loss function we designed for this problem. Modern deep learning libraries provide much more robust mechanisms for optimization. An optimizer like Adam, which we'll use in future lessons, would handle not only the loss function we developed for this lesson, but a huge class of other loss functions just as well. Going forward, we'll take advantage of the software engineering effort that has gone into making these machine learning libraries much more flexible and dependable. These libraries almost make it possible to treat optimization like a black box, requiring no human attention. But in practice, we'll see that this experience of developing our own optimizer will help us help the optimizer do more of what we want.